Hi everybody, welcome back. So today we are going to discuss the second property, which is the atomic size. Now the size of the atom can be measured in terms of the type of species it exists as. For example, if it is a noble gas, you have a particular type of the way in which you calculate the size. If it is an ion, there is a different type. So the most number of problems are usually asked from ionic radii. Please write the heading. Ionic radii. We'll be learning every one of them. But then let's start with ionic radii. Okay. Now, in case of ionic radii, let's say that you take any of the species. For example, NaCl, and you know that here Na exists as Na plus and Cl exists as Cl minus. Right. This is how it is. Correct. Now, actually, the ionic radii is the distance from the center of Na plus to the center of Cl minus. This distance is the ionic radii in total. That is how you measure the ionic radii, or you can say the internuclear distance. This is the center of the nucleus of sodium and this is the center of the nucleus of chlorine. So internuclear distance, so let me represent it as D, internuclear distance. Now, how can you calculate this D? It's very easy. All that you have to do is, you know that from the center of sodium to its periphery, it would be the radius of sodium plus, and from the center of chlorine to the periphery of the ion, it would be the radius of chloride. So the internuclear distance can be written as radius of Na plus radius of chlorine. Radius of Na plus radius of chloride. That is the internuclear distance. Now, the way questions come from this area is you will be given a series of species. Okay, so I start with oxygen. Let's start with oxygen. So let's say that I have three species: oxygen, oxygen plus, and oxygen minus. Okay, so in all these cases, the number of protons that are present, we know that the atomic number of oxygen is 8, and the number of protons that are present, whether it is oxygen, oxygen plus, or oxygen minus, is 8 itself. I hope you know that if it carries a positive charge, you call it a cation. So here, this is a cation of oxygen atom, and if it is negative, it is an anion. Correct? Now, when do you say that a species has become a cation? When it loses its electrons. So the neutral oxygen atom has got 8 electrons, but then when it becomes a cation, 1 electron is lost. Correct? Losing of electrons leads to the formation of cations. So now this is 7. And when you gain electrons, you get anions. 9. I hope you know that. If not, please write. So cation means it is losing electrons. You lose the electrons. And anion means gaining of electrons. Okay, this is how it is. Now, what you have to find over here is something called the effective nuclear charge. See, understand, over here, 8 protons. Now you know that protons are positive and electrons are negative. Right. Here, 8 protons bind 8 electrons. So the ratio is 1:1. Correct? Now over here, if you can see, 8 protons need to hold only 7 electrons. That means each electron is getting more positive charge. So what will happen? More positive charge will come if I take a ratio. Let's take a ratio here. Positive by negative, charge ratio is 8/8, which is equal to 1. So each electron will get 1 unit positive charge. This is just for your understanding. Okay. Now in the second case, if I see 8 divided by 7, what I get is 1.14 means each of the electron will get 1.14 of the positive charge. What about the next one? You have only 8 protons, but you have more than 8 to hold. You have 9 electrons now. So each electron will get only 0.88 of the positive charge. Now what will happen? When the positive charge which is felt by the electrons are higher, its forces of attractions are higher, right? Forces of attraction is very high. Correct? Why? Because there are only 7 electrons, and to control these 7 electrons, there are 8 protons. I'm sorry. But over here, there are 9 electrons and they are held by only 8 protons. So, if the forces of attractions are higher, they will be closely held. They will be close. So, if I have to give an example, let's say that this is my nucleus inside which I have 8 protons. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Let's say these are my protons. So in the case of a cation, the 7 electrons, I'm just pictorially representing them as they are very strongly adhered because there are only 7. 1, 1, 2, 3, 4, 5, 6, 7 will stay close because each of these 7 can feel a better force of attraction. While on the other hand, in the case of an anion, where you have 1, 2, 3, 4, 5, 6, 7, 8 protons, but it has to now hold 9 of them. So the forces of attractions will be slightly weaker and they'll stay a little bit apart, increasing the size. So can you get that if you compare a cation and anion with its own parent atom, the size, the order of size, the cation will be the smallest. Why? Because it is very closely held. Each electron has got more number of protons to attract. So the size of the cation will be smaller than the parent atom, whoever it is. And then comes the anion. This is the concept. Okay, this is very simply the concept. So in our case, it will be O minus less than oxygen less than, sorry, O plus less than O less than O minus. This is how it will be. Or very simply, what we can say is the size of an atom is directly proportional to the negative charge. Greater the negative charge, the size increases, and inversely proportional to the positive charge. Okay, so the cations are smaller than the parent atom and the anions are larger than the parent atom. So let's take another example of nitrogen. Now you please try to do it on your own. Let's say that I have N, N minus, N2 minus and N3 minus, let's say. And I want to see the size. So what will you do? First of all, you will calculate the positive charge, that is the number of protons and the number of electrons in each of these. The atomic number of nitrogen is 7. So the number of protons in each of these is going to be 7 itself, which is a constant. Now, if you look at the electrons, this is the parent atom. So this is 7. It is having one negative charge means there is one electron added. It becomes 8. Here, 2 electrons are added. That means 9. Here, 3 electrons are added, means 10. What did we say? Size is directly proportional to the negative charge and inversely proportional to the positive charge. Positive charge is to constant throughout, so we need to check only the negative charge, right? So size will be in the order of who will be the largest. The highest negative charge is for N3 minus. That will be the largest. Okay. Then N minus 2, N minus 1, and N. This is the decreasing order of size. Decreasing order of size. Let's do another example of cation. Let's say I have Ng, Ng plus, and Mg plus 2. Okay. So atomic number is 12. Number of protons is going to be 12 in all the case. But if you look at the number of electrons, what you can see is this is 12. This is cation. So one electron will be lost, will become 11. This is cation with a plus 2 charge, means 2 electrons will be lost and it will be plus 10. So you can see the largest number of electrons are present in Mg parent. Size is directly proportional to the negative charge and positive charge is constant. So we'll compare the negative charge. Correct. So this is order of size is the largest will be magnesium, then Mg plus, then Mg2 plus. This is the order. All right. Next question. Let's do a question where your order. So now we did questions where the number of protons are the same and the electrons are varied. Let's do an opposite one. Okay. Let's say you have Na plus, Ne, Mg2 plus, O2 minus, N3 minus, F minus, and aluminium 3 plus. You have to write the size. You have to write the size. Increasing or decreasing order of ionic radii is what you have to write. So, the number of protons will be equal to their atomic number. So here, sodium is 11, neon is 10, magnesium is 12, oxygen is 8, nitrogen is 7, fluorine is 9, aluminium is 13. Okay. Now, if you count the number of electrons, 1 electron lost, 10. No electron lost, 10. 2 electron lost, 10. 2 electrons are gained. So 8 plus 2, 10. 3 electrons added, 7 plus 3, 10. 1 electron added, 10. 3 electrons lost, 10. Okay. So if you can see, size is directly proportional to negative charge, which is a constant over here. But positive charge is varying and it is inversely proportional. Okay. So the one which is having the highest positive charge will be having the smallest size. They are inversely proportional. So which is having the highest charge? This one is having the highest positive charge. Correct? So the order of ionic radii, highest positive charge is for aluminium, so that will be the smallest. Aluminium 3 plus is the smallest. Then comes Mg plus 2, then 11 Na plus, then 10 neon, then F minus, O2 minus, N3 minus. Okay, instead of 10, you have to write neon. Yes. This is the increasing order of ionic radii. I hope you get it. Okay. So if you can see, the one with the highest cationic charges will be the smallest. And as the charge becomes more and more negative, the size increases. I hope you're getting the trend. Now, very important question. Let's say that your question is F minus, I minus, Br minus, and Cl minus. This is very easy. Why? Because if you take a periodic table, down the group, your size increases. Down the group, your size increases. So down the group, what do you have? Fluorine, chlorine, bromine, iodine. Even if they are anionic in nature, the trend is not going to change. So the order of ionic radii is going to be, fluoride is going to be the smallest, then chloride, then bromide, then iodide. Okay. Now, if the question is to write the order of fluoride, iodide, bromide, and chloride with H minus, Important. You cannot write this answer if you have not read it before. This was asked in IITJAM question paper. This is a pre-IQ. Very important. It is taken from the experimental data. So according to the experimental data, fluoride is the smallest. Then comes chloride, that is also fine. Then comes bromide. And surprisingly, hydride comes over here before iodide. Taken entirely from the experimental data. It is from a reference. So if you have not gone through this before and learned this exception beforehand, you will not get this answer. So this is very important. Okay. All right. So that is also done. So that is how you find the increasing order of ionic radii. Fine. Now, you also have to learn something called covalent radii. So this is where you get a lot of MCQs from. Now, the rest you can learn because if you're attempting any state level exams or any other exams like CET, assistant professor, etc., this would be of good use. Covalent radii. Covalent radii means, see, covalent molecules means they share electrons. Correct? Example, H2. So you have two hydrogens and they overlap to form the bond. And this is how you see a covalent molecule. So if you have a covalent molecule, there the internuclear distance, which we said, which is the center of this hydrogen to the center of the next hydrogen, this is the internuclear distance D. So how do we calculate it? D is equal to, from the center to the periphery, this is the radius of hydrogen. Correct? So you can see that from the center to the next periphery, this is radius of hydrogen. I can understand that there is an overlapping over here, which should be neglected. There is no way out. So what we do over here is, we neglect the overlap and we take the internuclear distance as RH by 2. Sorry. D is equal to 2RH. D is equal to 2 times radius of hydrogen, or the radius of hydrogen can be written as internuclear distance divided by 2, given that this shaded portion of overlap is neglected. Overlap is neglected. Okay. So this is all about covalent radii. This happens for Cl2, H2, N2, etc. Now you have something called van der Waals radii. Van der Waals radii. So van der Waals radii is when you have noble gases or real gases. So that is again of two types. Noble gases, like let's say helium. You have solid helium or argon. So let's say you have helium. You know the way it will stay is like this. Two heliums will not come more closer than this. So the internuclear distance over here is from the center of this helium to the center of the next helium. This is the internuclear distance. There is an empty space in between, which is again neglected over here. And what we write over here is from the center to the periphery, this is radius of helium. From the center to the periphery, this is radius of helium. And we write that the internuclear distance is equal to the radius of helium into 2. Or the radius of helium is equal to D by 2, provided you neglect the space. You neglect the space between the two atoms, two noble gases. So this force of attraction which holds two noble gases together is called van der Waals radii. It can also be seen in molecules like chlorine. You call it real gases. Or you can take hydrogen, whatever. Let's take hydrogen. You have hydrogen molecule and you have another hydrogen molecule over here. There will be a force of attraction between these two hydrogen molecules. Okay? So this H2, between H2 we know this is, between these two H, we know it is covalent radii. But between two H2 molecules, there can be van der Waals attraction. Okay. So here also there is an overlap. And we need to find, let's say this is H2. This is also H2. So they'll come close due to van der Waals force of attraction. So the center of this molecule to the center of the next molecule gives us the internuclear distance due to van der Waals forces of attraction. Okay. That's all you need to know, nothing much. So over here, you already know that the D covalent is equal to R of H2 divided by 2. Over here, it is also the same. Internuclear distance of H2 is equal to R of H2 divided by 2. Correct? Internuclear distance. Yeah. R of H2 plus R. It is 2R. Okay, it is opposite. R of H2 is equal to D covalent by 2. DH2 by 2. Both are the same, huh? DH2 is written as D covalent, which we have already written above. See, just above we have written. See, R of H is equal to D by 2. So you have H2, which is a covalent molecule. Between H2 molecules, you can see van der Waals forces of attraction. All right. So the next heading is metallic radii. Please write the heading, metallic radii. So under metallic radii, you can see two types of packing. Okay. One is square packing and the other, oh, my writing is not coming. Just a second. Metallic radii. Again, it's very easy. Metallic radii could be either square packing, wherein this packing of the metal atoms will form the shape of a square. So this, whatever I'm drawing over here, is a square packed lattice. Okay, so you can see now, this is a square, see? And hence this is called a square packed structure. So let's say this is some metal M. This is the radius of the metal. And you need to find the internuclear distance, D metallic. That is equal to 2 times R metallic. That's it. And in case of square packing, the way, this is square packing. Please write it down. This is square packing. And in case of hexagonal packing, you have something called hexagonal packing. There it will form a hexagon. That's all. You will be learning about this in detail in solid state. So 1, 2, 3, 4. And then the next set comes in between. Like this. Okay, this is how it comes. So can you see that this is forming a hexagon? Correct. And this is called the hexagon packing. And this is also very easy. This is the internuclear distance between the two atoms. Let's say I want to take this atom and this atom. This is my D metallic. And that is going to be again equal to 2 times my R metallic, where R metallic is the center from center of the atom to the periphery of the atom. Very easy. That's all. Now, if you have to compare the above radii that we have learned, very important, the biggest one is the van der Waals radii. as you can see that they have empty spaces in between them, correct? And we neglect. So there is a lot of empty space between them and we neglect that. And hence the van der Waals radii are usually the largest one, followed by the metallic radii where there is no overlap. And finally, you have the covalent radii. Covalent radii wherein you have overlap. We saw in the case of H2 that there is overlap. So because of which it is the smallest if we have to compare these three. Okay. Now again, you learned one exception about hydride. Similarly, you have to also learn one exception. Please write it as an important note, which is size of 3D series, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So this is how the 3D series looks like. This is 21 atomic number up to 30. You will have to learn it, no way out, because of which you cannot learn coordination properly. Okay. So usually the trend is as you move from left to right, your size decreases. If you move from left to right along a period, your size decreases because the electrons are being added to the same shell again and again. So they'll be closely pulled towards the nucleus and the size will be shorter, which we have learned in 11th, 12th classes. Okay. But here what happens is, see very carefully, the trend, actual trend is, the exception is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, and then there is an inversion like this. Very important. Very important. Why? Because up to this point, up to nickel, okay, up to nickel, you can say that as your effective nuclear charge increases, your size decreases. But in the latter two, copper and nickel, what happens is electron-electron repulsions start to dominate. And hence their size is slightly higher. What we expect is as we go on, this will also be smallest is what we expect. But no, there is a small change in the trend. And this exception is good if you learn because there is a high chance that they can ask this. Okay, so in inorganic chemistry, you get a lot of exceptions. So usually students find it very easy to learn inorganic chemistry. But then if you see any questions that you have not read before, please do not try to attempt it because you will end up getting negative marks. Okay. So just like you have a formula book for physical chemistry where you write all the formulas. Similarly, after each chapter, you can have just one page wherein you write all the exceptions. Exceptions in inorganic chemistry. Okay. So I think that is the end of the session. And in the next session, we'll be starting with ionization energy. Thank you.